Algorithm analysis. Welcome back to K-means. After we understood what the algorithm does, now let's analyze its operation. You will find there's more than meets the eye. Learning from mistakes. The K-means algorithm is an unsupervised machine learning algorithm that learns from its own mistakes. It first guesses a solution, the random centroids, then tries to validate it with its inherent mistakes, and then learns how to fix it, moving the centroids. Implementation. The number of clusters k must be provided. It must be known before running the algorithm. In many circumstances, this is not the case. A distance matrix is, of course, at the core of the algorithm. We can use Euclidean distance, cosine similarity, statistical correlation, or other metrics. The matrix is required in order to measure the distance between each point to a centroid, and also to compute a centroid based on a cluster of points. Adaptation and standardization. You may also want to manipulate the distance matrix so as to assign different weights to different variables. For example, if one variable's units are valued in the hundreds and another variable's units are valued in the tens of thousands. Or maybe the units and the values are equivalent, but you want to express that one variable is 10 times more important to you than the other. You get my drift. Complexity. This is a very fast algorithm. It usually requires very few iterations. But complexity isn't measured only by time. It is also measured by the required memory space. For example, the memory space required for the dynamic programming algorithm you saw for pairwise sequence alignment is in the order of magnitude of the length of the sequences squared. This is not the case here, as there is no real requirement for storing anything in the memory. So that's fantastic. Mathematical accuracy. Now, this is where things get tricky. As you remember, in the beginning, I said that many times this algorithm makes mistakes. It means that it does not assure optimal results. By definition, we want clustering algorithms that produce clusters where the intra-cluster distances are minimal and the inter-cluster distances are maximal. Does K-means achieve that? Does it assure optimal results? Do we know for sure that there could not be another clustering solution that's better mathematically than what was produced by K-means? Let's see. First, K-means has a stochastic element in it when it randomly selects the first centroids. Stochastic algorithms don't necessarily lead to wrong or non-optimal results. It could well be that although we start off at a random point in the virtual space of possible solutions, the computational process leads the result to the optimal point in this space. Is that the case here? Well, that depends on the properties of the solution space and on the search process to navigate in this space. These are more complex topics that we will explore later on. But for now, in the case of this simple algorithm, I think it's easy to realize that this algorithm is greedy. By saying that an algorithm is greedy, we mean that the choices it makes are based on a very narrow, short-sighted view, overlooking the big picture. This is what is happening here with K-means. At each step, it fixes the clusters, it improves them. That's all good and well. But does that guarantee that eventually we will reach the optimal state? Usually, greedy algorithms do not produce an optimal solution. And this is also the case here with K-means. In reality, in many cases, if we rerun the algorithm several times, each time with different initial centroids, we will see that we end up with different clusters. In summary, this method is often compared to the famous story of the Baron Munchausen, who saved himself from drowning by pulling on his own hair. In certain implementations of this algorithm, we can refer to it also as a sort of bootstrapping approach. Very similarly, bootstrapping is like putting real spur straps on boots in order to prevent the legs from sinking in mirror. Here, we change the clusters according to the centroids, and then we change the centroids according to the clusters, and then we again change the clusters according to the centroids, and so on. More about this bootstrapping approach in general later on in this course. For now, I just hope you see how pragmatic failures can be. So, enjoy your mistakes